Hello everyone. So this is the fourth video for chapter 9, and in this video we will see one tutorial problem. So we are doing with the example 9.2. So in this example we can read in a facility where detergent is manufactured, benzene is to be cooled from 51.7 degrees Celsius. So this is the initial temperature for the benzene, and it is required to be cooled by using water which is available at 18.3 degrees Celsius. So this is the available temperature for water. So this is the initial temperature for water. The process conditions require a benzene flow rate of, so the benzene flow rate is given 18.9 kg per second. The water flow rate is 22.68 kg per second. So basically both flow rates are given. Available for this service is shell and tube heat exchanger that has a shell inner diameter of 17 and quarter inches. So the inner diameter of the shell is given, which is 438.2 millimeter, and it contains 3 by 4 outer diameter. So 3 by 4 inch outer diameter tube, 18 BWG tube, and that are 4.88 meter long. So this is the length of the tubes. So the tubes are 4.88 meter long. So the tubes are laid out on a 1-inch pitch, which is 25.4 millimeter in triangular fashion, and the tube filled with the tube fluid make 2 passes. So the number of passes also given 2. The exchanger contains 10 evenly spaced baffles. So the number of baffles is given as 10. Analyze the proposed system and predict outlet temperature as well as the pressure drops. Route the benzene through the tubes. So the route the benzene through the tubes and use the following properties for the benzene. So here we can see that there are several parameters given in the for the design of shell and tube heat exchanger, and in this problem particular the design of the shell and tube heat exchanger is given, and what we need to do, we need to analyze it, we need to find the final temperature while finding the heat transfer coefficient, overall heat transfer coefficient, log mean temperature difference, and pressure drop, etc., etc. So basically we need to find the performance analysis of this. We have to carry out performance analysis and find out the performance parameters for this heat exchanger. So so for the analysis of shell and tube heat exchanger or any design problem of shell and tube heat exchanger, you need to have so many parameters, and these parameters, they are interconnected, so you have to be very careful about these parameters while doing the shell and tube heat exchanger problem. As for the properties of water and benzenes are concerned, then you have to apply the same approach what was applied for the double pipe heat exchanger. So when it comes to find out the properties, then you have to take the average temperature, and in case when the average temperature is not given, because this is given the inlet temperature for benzene and this is inlet temperature for water, so in that case you have to make a suitable average, and then you have to check after doing the complete analysis that the average was correct or not, and if not, then you have to repeat the your analysis. Okay, so here they suggested that the properties of benzene at 47 and 27 is this. So the assumption for this problem is again the same that what we did for the double pipe heat exchanger, that the process is steady state and properties remains constant throughout the length of the heat exchanger, and all heat loss by the hot fluid is equal to the gain by the cold fluid. Okay, so step by step procedure, if we see like we saw in double pipe heat exchanger, like step A, B, C, D, E, F, G, and so on. So the first step, you have to collect all the properties of the two fluid at the average temperature. So here are the properties of benzene, and these are the properties of water. In the second step, you have to write down the size of the heat exchanger. So what is the size of the, so first for the tube side. So what is the tube inner diameter? So the tube inner diameter is given tube outer diameter is given as 3 by 4 inch and 18 BWG. So the tube outer diameter is given that 3 by 4 inches, and that is the outer diameter. So the outer diameter 3 by 4, if you convert in millimeter, then it come out to be 19.07 millimeter, and BWG is 18. So for 18 BWG, we have to go to the table and then find out what is the thickness. So where is the BWG table? The BWG table is here. So this is for 1 inch tube and this is for 3 by 4 inch tube. So this is our case, 3 by 4 inch. And where is the 18 BWG? So here is the 18 BWG. So for the 18 BWG, and when the outer diameter is 3 by 4, the inner diameter is 16.6 millimeter. So now coming back to the problem, that the inner diameter is 16.6 millimeter. So the inner diameter is almost 16.6. This is the inner diameter that comes from the table, right? And the outer diameter, we know that it is 3 by 4 inches, which is 19.07 millimeter. And what about the distribution? The distribution is triangular and the pitch of the distribution is 1 inch. So this is 1 inch and triangular distribution. So for that, we need to go to the table and find out that how many tubes can be accommodated in the shell diameter of 438.2 millimeter. Okay, now we go to the table and then see that we have these 5 tables, like 1, 2, 3, 4, 5, these 5 tables. So what is that? This is for 1 inch outer diameter tube, so which is not our case. Our case is 3 by 4 inch outer diameter. So this is 3 by 4 inch and 1 inch, but this is square. So this is not our case. Our case is triangular. This is again a square pitch. So our is triangular pitch. So this is the 3 by 4 inch outer diameter and 15 by 16 inch triangular pitch. So in our case, the pitch is 1 inch. So the 3 by 4 inch outer diameter and 1 inch triangular pitch. So this is our case, and the shell inner diameter is 438.2. So this is basically is our point of concern, that this is the shell diameter and how many passes we have in the problem given. So the problem given shows that there are 2 passes here. This is 2 passes. So for the 2 passes, we have to see that how many tubes we have. So here we have our selection and number of passes are 2. So the number of tubes are 196. This is our number of tubes, 196. So the number of tubes are 196. So now we know that the inner diameter of the tube is 16.55 millimeter. Outer diameter is 19.07 millimeter. The number of tubes are 196 and the number of passes are 2. So here we complete the tube sizing. Now for the shell side, we know the inner diameter of the shell, and which is also called ds. So the inner diameter of the shell and ds, which is equal to 438.2 millimeter and 17.25 inches, right? And the length of the tubes are 4.88 meter, which is also the length of the heat exchanger. So we need to calculate the baffle spacing. So the number of baffles, we know that the number of baffles are 10. 10 are the number of baffles. So the number of baffles is 10, and then we can find the baffle spacing. So the baffle spacing is equals to the length over number of baffles plus 1. So here we can see that the inner diameter we know, and we know the baffle spacing, and so baffle spacing can be calculated using this expression. The number of baffles are 10, so baffle spacing comes out to be 0.445 meter. Now the pitch, it is given in the question that the pitch is 1 inch, 25.4 millimeter. And what is the clearance between the tubes? So the clearance between the tubes is pitch minus outer diameter of the tube, which is 6.33 millimeter. Now the next step is to find out the flow area for the tube side and the shell side. So we have the formula for the tube side flow area is the number of tubes and multiplied by the one tube area and divided by the number of passes. So if the number of passes of 2, then half of the tubes are taking and half of the tubes are bringing back the fluid to the same side. Okay. So when we want to find out the flow area for the tube side, then the number of tubes should be multiplied by the tube area and divided by the number of passes, which comes out to be 2.108 10 power minus 2 millimeter. As for the shell side, we discussed before that how to calculate the shell side area. So we are using the formula for the shell side area, and which come out to be 0.05 meters square. And remember here that when we say ds, the ds means shell inner diameter. So after that, the next step is to find out the velocities. So the tube side velocity, so the mass over rho A. So this A means tube area, AT, and so the rho and the A means AT, and here A means AS, and then we can find the tube side velocity come out to be 1.04 and shell side is 0.454 meter per second. And now we calculate the equivalent diameter for the shell. So the shell side equivalent diameter DE, and we have the formula for triangular pitch distribution, and then we can calculate the DE, which comes out to be 17.99 millimeter. So then we can calculate the Reynolds number for the tube side. So that, and we can substitute the values from the properties for kinematic viscosity, and the VT we just calculated, and IDT we know, and similarly we can calculate the Reynolds number for the shell side. The VS we just calculated, and the nu we know from the properties. Okay, so now we know the Reynolds number. So as we can see that this is a turbulent flow case, so we can use the turbulent flow expression. So remember here the tube side, the Nusselt number calculation is exactly same as in the case of double pipe heat exchanger. So the Nusselt number, we use the same expression as the expression in chapter 8 for the tube side, whereas for the shell side the correlation was given in this chapter, and this is the correlation for the Nusselt number for for shell side. Nu equals to 0.36 Re to the power 0.55 and Prandtl number 1 by 3 this is. And as for the tube side, we are using the same expression as in the double pipe heat exchanger. So after calculating the Nusselt number, which comes out to be for the tube side 154 and for the shell side 111. Now we can find out the heat transfer coefficient for inner side. We can use the expression as we used in case of double pipe heat exchanger, and after calculating HI can be changed into the tube heat transfer coefficient by using the formula as we did in double pipe heat exchanger, and then we can calculate the shell side heat transfer coefficient H0, and which comes out to be 3725 watt per meter square. Now if your heat exchanger is new, then you can calculate the overall heat transfer coefficient without taking the falling factor into account, and when you substitute the value, it come out to be 835 watt per meter square Kelvin. Okay, we know the length 4.88, and we know the number of tubes, so we can find out that what is the heat transfer area. So the heat transfer area is number of tubes multiplied by the heat surface area from one tube. So it come out to be 57.25 meter square, and remember that it's outer surface area of the tube. We can calculate the capacity ratio. So R equals to the cold fluid capacity over warm fluid capacity. When it comes out to be the C, then the C means the minimum capacity divided by the maximum capacity. When the R value is more than 1, that indicate that the W is minimum, and C and warm fluid is minimum, and the capacity of cold fluid is maximum. So we can calculate the C, which is basically inverse of R in this case. And then we can calculate the number of transfer units, which is equal to U multiplied by A. A means this area. and U means this overall heat transfer coefficient here. Okay, so we can calculate the number of transfer unit, and which comes out to be 1.44. So this MCP min we can take from here because the R value is more than 1. So this is basically your MCP min. So this can be substituted here. Okay. Now we can calculate the effectiveness E for the heat exchanger, and we can substitute all the value in the expression and we can get this, and it come out to be 0.666. Alright, so now we can decide that which set of formula we can use to find out the outlet temperature based on the effectiveness and C, based on E and C parameters. So as we know that the warm fluid capacity is lower than the cold fluid, so we are using the set of formula as per this condition, and which is T2 equals to T1 minus E, T1 minus T1, and T2 equals to T1 plus C, T1 minus T2. So when you substitute the value in the T2, so T1 we know, E we know now, and then T1 and T1 we know, so we can calculate T2, so which come out to be 29.4. And then we can calculate this is small T2, which come out to be 26.1 degrees Celsius. So we know all the 4 temperatures now. Now we can calculate the log mean temperature difference. So after substituting this, so remember here the log mean temperature difference in case of shell and tube heat exchanger is always counterflow. So which comes out to be 17.33 degree Celsius. So the heat loss by the warm fluid, we can calculate MCP dt for the warm fluid, and heat gain by the cold fluid we can calculate also by MCP dt, and this must comes out to be equal. Okay, now for the heat exchanger performance from the rate of heat transfer from the heat exchanger performance parameters. Okay, so the overall heat balance for the heat exchanger which is Q is equals to U naught, A naught, and F and LMTD. So the LMTD we know now, this is our LMTD, but the correction factor F we don't know. The U naught we know and A naught we know. So for the correction factor F, F is a function of S and R. So we need to find out what is our S and we need to find out what is our R. And then when we have S and R, then we can go to the figure 9.12. So here we have our figure 9.12. So now we can see the value of correction factor. So based on the R value, so R is 2.843 and S is 0.234. So we can go to the chart and we can find that this is the S scale, and then this is the R scale, and this is our point of interest here. So this point is around 0.89 something. So this is the value of F now. Okay, so when we substitute this value F here, and then we can find that the rate of heat transfer come out to be 7.4 10 power 5, so which is equal to these two values. Okay, so here our thermal analysis is complete now. So we know the final temperature and we know the rate of heat transfer, and we know the effectiveness of the heat exchanger. Okay, if you take into account the Fouling factor, then the overall heat transfer coefficient will be changed, and this is the way that how you take into account the Fouling factor. So your new overall heat transfer coefficient is 664 watt per meter square Kelvin, and based on this new overall heat transfer coefficient you can go back and then you can basically calculate that what is your number of transfer unit, and with the help of the new N calculation you can go and calculate the new effectiveness E, and then based on the new E you can calculate the T2 and T2 again. So when you calculate the T2 and T2 again, then this come out to be 37.1 and 25.5 degree Celsius. So when you have taken into account the falling factor, that means that your heat exchanger will give this performance even after 1 year. Okay, so here we complete the thermal analysis of the heat exchanger. Now come to the pressure drop. As for the tube side pressure drop is concerned, it is exactly same as the double pipe heat exchanger. The only difference is that here we need to take into account the uh, the turning effect, that is the minor loss effect in the tube side, and which is 4, and the length of the flow path will be multiplied by the number of passes. So when we calculate the tube side pressure drop, it is equals to 1 by 2 rho bt square, and then FL ID plus 4, and this whole is multiplied by the number of passes. So the first term, this is indicative of the friction pressure drop, and this is the pressure drop due to the minor losses. Okay, so the friction factor we can calculate based on the RE of the Reynolds number, and based on the epsilon over D, and which comes out to be 0.024. Okay, as for the shell side, we have correlation for friction factor based on the RE, so we will use that correlation for the shell side. So the shell side friction factor, we will use this correlation, and which is valid for Reynolds number greater than 400 up to the 1 million. So in our case, the Reynolds number for the shell side is 8000, so we can use that expression, and the friction factor for the shell side come out to be 0.319. Okay, now for the shell side pressure drop, so this expression we discussed in our previous lectures, and that so the length of the flow path is ds multiplied by nb. Basically the length of the flow path, this is ds, and multiplied by nb, number of baffles, and plus 1. So this ds, and then multiplied by the number of baffles plus 1, this together makes it L, length. So the 1 by 2 rho v square multiplied by the length divided by the equivalent diameter and multiplied by the friction factor. So it gives the pressure drop expression, and the pressure drop comes out to be 8.8 kilopascal for the shell side. So now we have done the hydrodynamic analysis of the heat exchanger. So the as a summary of the information that until now we have analyzed. So when our heat exchanger is new, then these are the performance parameters, and when our heat exchanger will be old, then this is the performance parameters. So in this case we have taken into account the falling factor, but when it is new we have not taken into account the falling factor. So the initial, okay, so this is how we can tabulate the summary of the our calculations, and then we can see that. So the as for the pressure drop, the both side pressure drop is less than 70 kilopascal. So the 70 kilopascal, we take it as a industrial pressure constraint, that the heat exchanger should not make more than 70 kilopascal pressure drop for both side, either tube side or shell side. So this is the complete analysis for the shell and tube heat exchanger. So we started with the properties, that we have all the properties, and then we go step by step, sizing the tubes, sizing the shell, and then calculating the areas, and then calculating velocities, and then equivalent diameter, Reynolds number, Nusselt number, and then heat transfer coefficient, overall heat transfer coefficient, and then with the help of C and N we calculated the effectiveness, and using the effectiveness we can find out the final temperatures of tube and shell side fluid, and then we can calculate the log mean temperature difference. And after having all these things, we can equate the rate of heat loss by warm fluid equals to the rate of heat gain by cool fluid, and this is also can be calculated with the help of heat exchanger parameters like correction factor, LMTD, overall heat transfer coefficient, and surface area, and which comes out to be the same. And this is the formula that we can use to find out the uh, correction factor F with the help of R and S, or we can directly use this chart. So this chart, we need R and S, and then we can calculate the friction factor also. Sorry, correction factor also. And if you taking into account the falling factors, then you can revise your overall heat transfer coefficient, and that will indicate that your heat exchanger can be workable even after 1 year. And then you can find out the new temperatures. You can find the tube side pressure drop exactly the same way that you did for double pipe heat exchanger or before you did for pipe network analysis. When we suggest the delta P for the tube side, then we take into account the minor losses factor 4 in multiplication with the number of passes. And for the shell side, the ds multiplied by this ds multiplied by number of baffles plus 1, this is basically your L, the length of flow path that is subject to the or we call it friction length. Okay, so here we calculate the pressure drop, and then we can summarize all the information that that is related to the heat exchanger. What is inlet temperature, what is outlet temperature, what is pressure drop, what is overall heat transfer coefficient, and what is the rate of heat transfer. Okay, so this is all about the this problem. One more thing is that at the end we need to check that our pressure drop should not exceed 70 kilopascal, which is industrial constraint. Okay, so this is all about the analysis, and hope you understand this. And then on the next video we will see that how we can go for a design problem. Thank you so much.